Then I shall invite the first speaker, and that is Associate Professor Reidar Gautun from Organic Chemistry in our department. And he has been working on different things. First of all, he's been working on stereoselective methods in organic synthesis, and also asymmetric catalysis and organometallic chemistry. And then today he's going to talk to us about retrosynthetic methods, more general introduction. And please help me welcome Reidar.
Okay.
But do you need this one?
Okay. I also need help to get my...
This?
Okay. You hear me? Space. Good morning, and thank you for the kind introduction. The title of my lecture today is Designing Multistep Organic Synthesis. The content of my talk will be this. First, starting with an old history about tropion synthesis. Then I will continue with linear and convergent synthesis. Introduce the concept of retrosynthetic analysis, and then I will use one recent example from the literature, the total synthesis of protectin D1, to illustrate the concept. This overhead shows some of the most complex natural products synthesized to date. The book Classics in Total Synthesis, written by K.C. Nicolaou and E.J. Sørensen, describes how some of the world's greatest synthetic chemists planned and performed their total synthesis of complex natural products. Some of the synthesis presented in the book consist of more than 30 synthetic steps. How is it possible to plan and perform a 30-step synthesis? I hope this lecture will give you some idea how this is possible. In 1901, Richard Wildstetter published the first total synthesis of tropinon, an alkaloid sharing the same tropan core structure found in atropine and cocaine. This tropinon is also a precursor for preparing atropine and cocaine. Wildstetter did that at that time. Wildstetter tropion synthesis does not involve any CC bond formation. The choice of the start material was probably made by the analogy of the product. And in the expectation that one 7-membered ring, cycloheptanone, could be converted to another of the same structure. Synthesis design by this approach usually means that the choice of starting material dictates or restricts the choice of strategy. As you see, Wildstetter's synthesis required many steps just to introduce this nitrogen bridge. The overall yield for this synthesis path was only 0.75%. The 1917 synthesis by Robinson is considered as are classic in total synthesis due to its simplicity and biomimetic approach. Citing Robinson in his analysis, by imaginary hydrolysis at the points indicated by the dotted line here, the substance might be resolved into succinyldialdehyde, methylamine, and acetone. And this observation suggested a line of attack of the problem which has resulted in a direct synthesis. Here, tropion was synthesized in one operation by heating an aqueous solution of 3 simple starting materials in a double Mannich reaction. As you see, the yield was 17%. Recent work by others has raised the yield up to 90% just by adding some buffer to the reaction solvent. The analysis of this synthesis is dictated primarily by the structure of the target molecule, not by consideration of possible starting materials, and is therefore regarded as an early example of what nowadays is called the disconnection approach or retrosynthetic approach to synthesis planning. Before I start to talk more about retrosynthetic analysis, I will first introduce the concepts of linear and convergent synthesis. In a linear synthesis, the starting materials are linked sequentially. If the number of steps is high, the overall yield will be low, even if each step gives a high yield. In this 7-step synthesis, where each step is 8%, the overall yield will be only 21%. For a 70% yield at each step, the overall yield would only be 8%. One important example of linear synthesis is Merrifield's peptide synthesis, coupling amino acid in a direct associative approach. It's not uncommon that more than 30 amino acids are coupled by this method. Convergent synthesis involves the separate assembly of large fragments of the target molecule. These fragments are then joined at the latest possible stage of the synthesis. Here, the synthesis involves 3 stages, and with each step in 80% yield, that should give an overyield of 51%. Another important consideration is that a convergent approach is that failure of a single step in a multi-step synthesis does not nullify the chosen synthetic approach as whole, whereas a failure of a single step in a linear scheme might require a revision of the whole plan. The concept of retrosynthetic analysis has been developed and described in detail by E.J. Corey in this book, The Logic of Chemical Synthesis. This book is rather advanced and for experts. For teaching at the university, I will recommend Stuart Warren's book, The Disconnection Approach, first time published in 1982. I have heard Warren giving lecture twice. He is probably the best lecturer I have ever heard in organic chemistry. This is the old edition. There are new editions on the market today. I know that he has published one book together with Paul Wyatt from Bristol University. Retrosynthetic analysis, citing CORE, a problem-solving technique for transforming the structure of a synthetic target molecule to a sequence of progressively simple structures along a pathway, which ultimately leads to simple or commercially available starting materials for a chemical synthesis. So that means the target molecule, TM, is taken apart by a series of bond disconnections or retrosynthetic transforms, as shown here. A retrosynthetic transform is thus the exact reverse of a synthetic reaction, and imaginary cleavage of a bond to break the molecule into a simpler starting material. This double arrow describes a retrosynthetic transform. Transforms create syntons, which are idealized fragments, usually anions or cations, as shown here. And the synthetic equivalent of a synton is the reagent, and in this case it's methyl iodide for the cation. A retron is a structural subunit present in a target which allows application of a given transform. The retron for the Diels-Alder transform is thus a six-member ring containing a p-bond. This is just to show you that there are other types of transform, not only disconnections. Here you see example for connections. A retrosynthetic connection joins up a bond which is broken in the synthesis. And here the target is a 1,6-D functional. You can get that from this Diels-Alder retron, which you again can get from these reagents. And then you have retrosynthetic rearrangement, here illustrated by the Bayer-Williger rearrangement. So the reaction itself goes from here to here. You have also a Beckmann rearrangement, which is also important rearrangement reaction. You also have other types of transformation. You have something called functional group interchange, which refers to replacement of one group to another, like going from carbonyl to the alcohol. Functional group addition, then you add some extra group here. Functional group removal, then you just remove one group. Or functional group transposition, then you just change position of that group. Okay, the whole point of retrosynthetic analysis is to achieve maximum simplification of the problem. Strategic disconnections of strategic bonds are those which lead most effectively to retrosynthetic simplifications. And the strategic bonds are usually those for which many reliable methods exist for their formation. These bonds are disconnected first in the analysis and thus formed last in the synthesis. And that's important. You should have a good reaction at the end of the synthesis. Okay, here I will show you some guidelines for good disconnection I have received from Professor David Tanner from DTU. And the first point, make the synthesis as short as possible, is rather obvious, I guess. You agree? You should consider very often you need to use protecting groups. You should remind yourself that gives you 2 extra steps. But with very high density functionalized compounds, it's very difficult to avoid that. The optimum is a disconnection which gives two identical fragments or two fragments of roughly equal complexity. And here you see one example where this ring is broken to two parts, and you can just see how that happens the synthetic way, just an SN2 reaction here and lactonization here. The third point, simplify rings by disconnection of side chains. And this is a very excellent example, published by Noyori, but also I think Corey is also was the supervisor for Noyori in this case. This prostaglandin synthesis, which is a one-pot synthesis, where the protecting group here controls the stereochemistry of the incoming cuprate here, microaddition. And then this group will point in the opposite direction of this one, pointing up, and then the enolate, after some transmetallation to a tin compound, from copper to tin, you have alkylation on this side, and that should be at the opposite side of this group. So this group points down. And I know that some of the people from the audience have seen this before in my course in organometallic chemistry. Okay, strategic bonds are often those two heteroatoms, like you see in ester, amide, imine, acetal bonds, which are easy to form. For acyclic systems, disconnect at the branch point. This should give us straight chain fragments, which are normally easier to obtain. Strategic bond often directly link two rings. So here we also can see how they are connected. It's just a Michael addition. Another rule is do not disrupt aromatic rings in the target. If you do that, you will probably get some problems. Polycyclic systems, fused rings, disconnect to give two equal fragments. And here you see the, retron for aldol condensation. So it's natural to cleave here. And then you have this you can obtain from a double Mannich reaction. Sorry, Michael addition. And if possible, make use of symmetry. That should simplify the synthesis. I have chosen a recent total synthesis of protectin D1 as an example to illustrate the concept of retrosynthetic analysis. Reidar Gautun and his group at the University of Oslo published this excellent work in 2014. Protectin D1 is a polyunsaturated fatty acid with potent anti-inflammatory properties. Some points about the structure of PD1 were given in the paper. PD1 contains a pair of two chiral secondary alcohols, here and here, which are allylic or homoallylic, unlikely to be labeled and prone to dehydration either here, here, and here, making the conjugated olefin. The E set moiety in the middle here will need to be constructed in a stereo-controlled manner and preferably at a late stage in the synthesis. And then you have two cis double bonds which are not in conjugation, should be constructed in a highly selective manner. From this, the following retrosynthetic analysis was proposed: a disconnection to 3 fragments of similar size, A, B, and C. The conjugated cis-olefin here may result from a set selective hydrogenation of the corresponding alkene, which in turn can be disconnected between C14 and C15. The latter bond might be formed in a Sono-Gashira coupling between here and here. The C7 and C8 cis double bond might be obtained from a cis-selective Wittig reaction from this side and this side. The synthesis of fragment A was already published in the literature in 6 steps from precursors A1 and A2 and adopted in this synthesis. Fragment B to have this beta hydroxy carbonyl moiety, which is the aldol retron, and may therefore be cleaved between C9 and 10 with the intention of using an asymmetric acetate aldol reaction in the synthetic direction. Fragment C was disconnected between C5 and C6 to give C1 and C2. Only the successful part of the synthesis will be shown in this lecture. This slide shows the synthesis of precursor of fragment B. The first part of synthesis to B1 was an adapted synthesis, literature synthesis, where I open this pyridine ring in a basic condition to give this conjugated aldehyde, and this group is then replaced by brom. The synthesis of the enantiomer B2 is also a literature synthesis, and I will not go more in detail about that. B1 and B2 were reacted by addition of a Lewis acid and Hünig's base, and that afforded a diastereomeric mixture of 2 aldol products, where the major product was the wanted product. By doing a flash chromatography, they were able to isolate this one pure in 86% yield, and then this alcohol was protected with a silyl group. C2 was treated with 2 equivalents of N-Buli. The first equivalent will remove this proton, and then the second equivalent will remove this proton. And this anion will be the reactive reaction center for attacking ethylene oxide, affording this product. The synthesis continued with esterification, and then this triple bond was reduced by linear catalyst to this cis-olefin. The alcohol function was replaced by iodine using this Apple reaction. And finally, the phosphor part of the molecule was introduced by an SN2 reaction. The assembly of fragments A, B, and C, and the final steps toward the PD1 is shown here. The label and fresh aldehyde B was reacted with fragment C in a set-selective Wittig reaction. After chromatographic purification, none of the undesired E isomer was detected. Next, a Solo-Gashira coupling, cross-coupling with A afforded the desired intermediate shown here in very high yield. The protection of the silyl protecting groups afforded the diol, and then they reduced this triple bond to the cis double bond. And here they had some problem, but after some trial and errors and some improvement of existing methods, they were able to make this cis olefin using the standard linear catalyst, but they added also this 1-octene, without not giving any good explanation for that. At the end, they did this hydrolysis, basic hydrolysis, and I got the product in 14 milligram product. Okay, here you see proton NMR of the product, which was in accordance with literature data. Very nice. But maybe more convincing is to see the carbon-13 NMR spectra, as you see here, where one peak here represents one carbon in the skeleton of the product. This example demonstrates high knowledge in synthetic chemistry. You need to have some guts to start projects like that. And I guess Hansen's group is one of few, I guess, maybe he's the only, no, there are some more. But he is one of few professors in Norway doing total synthesis of natural products. You need also the manpower to perform the synthesis. Here exemplified with two highly skilled experimentalists, Dr. Marius Aursnes and Dr. Jørn E. Tungen. At the time this paper was published, they were both PhD candidates. Tungen did his master here at NTNU with Professor Anne Fiksdal as supervisor. So we educate good people. With this, I will finish my lecture. Thank you for your attention.
Thank you very much. We'll take some questions.
Yeah.
At slide 28, the chiral auxiliaries with
Here.
Yes, the two sulfur atoms instead of oxygen.
Yeah.
What's the reason they use?
You know, this reaction goes through the Zimmermann-Traxler transition state model. And with sulfur, you have a tighter transition state and better stereo control.
Oh, sorry. More questions? I have a question.
Yeah.
And is it possible to automate this? Because when I see these transforms that you talked about,
Yeah.
how easy would it be to make a computer program to search for that?
Oh yes, there are computer programs for this. Corey has developed a computer program called LASA. I think it is in its 18th edition now. I don't know these programs, but I think they are good.
Okay.
Yeah.
So these programs are
They do retrosynthetic analysis.
they give you a complete pathway.
Yeah, but you need to be a skilled organic chemist to understand what you see and say if this is a good proposal or not. You have to be organic chemist, and you have to know lots about the organic reactions. More skilled you are, better chemist you are. So not everything can be solved by a computer. I don't know. But the hard work is what you do in the lab. Yeah. Yeah.
I'm curious about the lambda reduction. What kind of trouble, do you know what kind of trouble they encountered? What's they have 65% yield, so what
It could be degradation and things like that. You have in this molecule you have several skipped olefins. That means you have isolated olefins, and they are very prone to move to a conjugation and so on. So you have other problems.
Okay. We have another question from Board.
When you look at the literature and people present retrosynthesis, sometimes it can look quite impressive. But in how many cases do you think they have come up with the retrosynthesis in retrospect?
Okay. When you start, you should at least have some idea where to start. And very often, the first approach didn't work. So then you have to do something. When you are working with this, the plans will be changed. So of course, it will be, in many cases, it will be in retrospect. Yes.
Okay.
If you are not Corey, then.
Any more questions? If not, we thank the speaker again.